Hello everyone. This is the presentation of Mechanism Sessional Group project, for which we have decided to synthesize and simulate the windscreen wiper mechanism with no quick return effect. Our team members are Chethan Girish, Siddhapura Om, and G.V.K.Sai Sarath. This presentation comprises of mainly three parts. First one is synthesis process, second one is MATLAB computation, third one is SolidWorks, 3D simulation and analysis of the mechanism. I, Siddhapura Om, will be explaining how we graphically synthesize the mechanism. For synthesizing the mechanism, we have used the overlay method. We have taken the length of input crank to be 2 cm and the length of the fixed link to be 6 cm. On trying to synthesize the mechanism for input angles 30 degree, 90 degree and 150 degree and the corresponding output angles to be 40 degree, 90 degree and 140 degree, we get the length of output link to 2.4 cm and the coupler length to be 6.5 cm. But this does not satisfy Grashoff's law. On increasing the length of the link to 2.5 cm, it satisfies the Grashoff's law, but wiper goes below the reference line. Evidently, with these dimensions of the output and a coupler, we get the maximum area covered by the wiper. On scaling up the link lengths by a factor of 2 to the required dimensions, we set the input link lengths to be 40 cm and the output link length to be 360 cm and the length of the fixed link to be 120 cm and the length of the coupler to be 130 cm. For the innovating part of our problem, we have added another wiper at the other end of the same linkage of the mechanism in order to increase the area of wiper. Now my teammate will continue with the MATLAB computation part.
Hello everyone, my name is G.V.K.Sai Sarath. I will be taking the presentation forward from here on. I will be discussing the simulation part of the project, that is, the MATLAB code for the mechanism. We have entered the required link length after graphically synthesizing the mechanism. Here, the length of the clank, length of the coupler, length of the output link and the length of the fixed link have been entered. Also, the value of E here denotes the length of the longest link in the parallelogram linkage. This value indirectly affects the wiper area. We have then varied theta from 0 to 3600. That is, we have given 10 rotations to the crank and converted theta to radians. We have calculated the various lengths and angles required to locate the position of the output link. Here, R, S, U, V, M, N, O, and P are the various points on the wipers required for tracing purpose. We have attached the wiper plates of the 4-bar parallelogram linkage, which is welded to the output link of our 4-bar parallelogram linkage. In the next section, we have plotted the mechanism and its various traces for marking out the area wiped. Calculation of output angular velocity and the output torque for a given motor specification can be done using the velocity and the force analysis respectively. Generally, the torque required for the wiper blades to move ranges from 20 kilonewtons to 30 kilonewton meters. We have deleted our links for the next iteration and plotted them to bring back the mechanism to its initial position when the loop ends. Thus, we have synthesized a windshield wiper mechanism with no quick return effect. Now, I will run the code and show you the actual simulation. As you can see, the blue area that is being wiped by the wiper is the actual area that we are required of. Here, the red link denotes the crank link, the black link denotes the fixed link, the green link denotes the coupler link, and the yellow link denotes the output link. This yellow link of the parallelogram linkage is essentially a part of the output link only. This particular pink link will define the area wiped by the wiper. As you can see, our code is successfully plotting the blue area wiped by the wiper. Now my friend Chethan will take the presentation from here on. Thank you so much.
Hello, I'm Chethan Girish and I will be explaining the SolidWorks 3D simulation and analysis part. So the first step in this was sketching the 2D mechanism. The second was about the designing the 3D linkages for the mechanism, taking the reference of the 2D sketching. And then we ran this assembly on the SolidWorks motion simulator for its analysis. The fourth part was studying the results of the simulation through motion plots. Now coming to SolidWorks for the working of the simulator. So the first part of the process was the 2D sketching. So in the 2D sketching, we just made the 2D sketch of the mechanism as synthesized and applied the length constraints and angle constraints to ensure the proper motion of the mechanism. After verifying the mechanism synthesized, we then moved ahead to make the 3D CAD of the linkages. The 3D linkages can be seen here. Now I'll be showing the motion, which can also be seen in an isometric view. Okay, now moving on to the motion analysis. So there's an option in SolidWorks called SolidWorks Motion. Now we use this add-on to animate and get the analysis reports of motion. So while using this, we first added a motor. The motor can be seen here. Now the features that we added in the motor were we added the motor on the inner surface of the crank linkage with 24 rotations per minute, which would ensure uh, 2 revolutions per 5 seconds. We also applied a motion plot to find the trace of the wiper ends, which you can see as black lines over here. Now coming to the motion analysis. So basically we just right click on the part. We can just see this option called create motion plot, which would take us to this place where we can choose any of these categories. Let's just say displacement velocity for now, linear velocity, and its magnitude. We then select a face of the component which we want to calculate the linear velocity of. Click select and then we go for calculate. You can see the motion here and then we get plot. Cool. So we have made various such plots for various linkages such as crank, coupler and the output linkage. We have calculated the required torque by the motor and we have put it in the PPT. I'll be moving on to that. The analysis results. The first plot shows us the plot of angular velocity of the crank. It is clearly constant at 144 degrees per second due to the constant 24 rotations per minute provided by the motor. The second plot shows us the required motor torque for maintaining the constant rotations per minute at the crank. You can see that the peaks or extremities occur at 0.5 and 1.5, which show the dead center configurations. You can clearly see which is stable and which is unstable by the motor torque required. Coming to the next plots, that is linear velocity and linear acceleration plots of the coupler. And then we have the results for the linear velocity, linear acceleration, angular velocity, and angular acceleration of the output linkage. Thank you.